What's cooking? In this lesson and the next, we're going to see both parts of the fundamental theorem of calculus, which connects the two main branches of calculus, derivatives and integrals. It is one of the most important theorems of mathematics because it connects two seemingly different problems, finding the slope of a curve and finding the area underneath the curve. Now, since it's such a big theorem, we're going to spend 2 lessons covering it. And I want to look at the first part now. And to do that, we need to look at a particular type of function. The first part of the fundamental theorem of calculus deals with functions defined in the following way. So we'll have a function g of x. And instead of being given a nice, easy expression for it, g of x is going to be written as an integral from a to x of f of t dt. So we're going to be looking at functions that are defined as the integral of another function. Now, if this was an integral that had constants as the lower limit and the upper limit, we know that we would take the integral and we would get a number. We would just have a constant, and that wouldn't be a very interesting g of x. It would just be a constant function. But if we're looking at an integral from a up to some quantity x, then the value of this integral depends on what x is, and that means this whole thing is a function of x. Now, this is maybe a little bit difficult to wrap your head around, but there is a nice way to look at it, particularly if our function f of t is always positive. We can consider this function to be the area so far function. Let me show you. Suppose this is the graph of our function y equals f of t, and it's defined on a closed interval from a to b. Then if we're looking for any value of x that's in between a and b, basically that's somewhere in our domain, and we look at the integral from a to x of this function, what that gives us is that gives us the area of the region underneath that graph if we're looking between a and x. So that integral on the right-hand side up above, the integral of f of t dt as t ranges from a to x, is basically the area of this region, and it depends on x. If we increase x, then that gives us a larger region and it gives us more area. And so basically, this area is represented by g of x. That's what that function gives us, and it depends on the x value. If we pick a different value of x, that's going to be a different area, and thus that area is a function of which x we choose. Let's look at a more concrete example. Let's actually look at something where we know what our f of t is. Let's say g of x is equal to the integral from 0 to x of t dt. Let's look at this function. Now, this function, y equals t, where t is kind of takes the place of our x-axis, and then y is the y-axis. This is a linear function, y equals t. You can think of it as y equals x if you're struggling with t. We know that that is a diagonal line that goes through the origin and heads up at a 45-degree angle. This is our f of t equals t. And if we're looking at the integral from 0 to x, that means we're looking at the region starting at 0 and going up to some value x. We don't know what that value is going to be necessarily. And the integral ends up giving us the area of this region. I hope you're shading along. It is delightful. Okay. And so we don't necessarily know how to take this integral, but we certainly know how to calculate the area of a triangle. This triangle has base equal to x, and the height is also equal to x. Because remember, the height was our function f of t equals t, and if the input is x, that means the output is x. And we know the area of a triangle is 1/2 base times height. And in this case, the base and the height are both x's, so that's going to be 1/2 x squared or x squared over 2, either way. So that's the value of g of x. G of x is going to be x squared over 2. That's the area so far function. And I want to point out something interesting about this. If we look at this function and we take the derivative of it, g prime of x, well, we know the derivative of x squared is 2x, and when we divide that by 2, that just gives us x. So the derivative of this function is just x. And the original function that we started with, f of t is t. If we compare those two, I'm going to highlight them just so that we can look at them. F of t equals t and g prime of x equals x. Even though these are using different variables, these are effectively the same function. These are both the function that takes the input and returns it as the output. And so the thing I want to point out is g of x was defined as an integral of f of t. And so if we take f of t and we integrate, we get g of x. And then if we differentiate, we get g prime of x, which is effectively the same function that we started with. So we started with a function, we integrated that function, and then we differentiated the result, and what we ended up with is effectively what we started with. And that is what the first part of the fundamental theorem of calculus tells us. The fundamental theorem of calculus, part 1, says that if f is continuous on the closed interval from a to b, then the function g, defined by g of x, equals the integral from a to x of f of t dt, where x is between a and b, is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, and the derivative of g of x is equal to f of x. So that's saying if we're looking at this function that's kind of the area so far function that we get from integrating f of t, then we take the derivative of that, we end up getting the original function f of x out. It's with x instead of t, but that's not a big deal. There is another way to write this with Leibniz notation that I like even more than this. It's a lot simpler. This says that if we start with our function f of t and we integrate it from a to x, which turns it into a function of x, and then we differentiate with respect to x, we end up with that original function back, though in terms of x instead of t. In other words, if we take the integral and then we differentiate, those two things effectively cancel each other out, and we end up with our original function. Now, I am not going to go through and give you a formal proof of the fundamental theorem of calculus, part 1. If you want that, you can find it online. They exist. But the reason I'm not going to do that is because I don't think it's really going to help you understand why this is true, and I would rather spend some time talking about intuitively why this makes sense. Now, this whole thing effectively boils down to the fact that g prime is equal to f. When we integrate f to get this new function g and we differentiate it, we get the original function back. And remember that G is the area so far function. So what this says is the rate of change of area is equal to the value of the original function, right? We know a derivative is a rate of change, and this G is the area so far function. So the rate of change of area is equal to the original function. Well, if we look at this function here, this first example, and we think about the area so far, in this particular case, anytime x is increasing, the area ends up increasing. And so the rate of change is positive, right? When something is increasing, that's a positive rate of change. And that's because the function values are all positive here. If it dipped below the x-axis and we had a negative function, then we would start getting negative area as a contribution, and the area function would be decreasing. So we see that negative function values give us decreasing area, and positive function values give us an increase in area. And of course, the larger the function value gets, the quicker the area is increasing. So we can see that the size of f tells us how fast the area is going to be changing. When it's positive, the rate of change is positive. When it's negative, the rate of change is negative. When it's much, much, much larger, the rate of change of area ends up being much larger. The area is growing faster. And so intuitively, we can see how these things are related. If you want a proof of all of this, which gets a lot more technical and deals with a lot of algebra, and it's less intuitive, but it is a formal proof, you can find that online.